Hello, everyone. I'm Liu Pan from D2S. The title of my talk is Enabling Faster VSB Writing of 193i curvilinear IoT masks that improve wafer process windows for advanced memory applications. This is a joint work of D2S and Micron Technology. Last year at this conference, I presented our first paper on curvilinear IoT. That mask was written by multi-beam mask writer. I showed you this movie is a sequence of 91 different contact array, 11 by 11. Each one, we just slightly change the pitch and the rotation, and we put them together into a sequence. On the left is the mask SAM image, shows the mask pattern written by multi-beam mask writer. And on the right is a wafer printed using that mask. We demonstrated we actually produced over 100% larger process windows than OPC. And all of those was done by our true mask IoT, which satisfy all of the manufacturing requirement. It can do a full chip IoT in a day. It doesn't have the stitching issues that normal IoT product has. It generates those curvilinear mask features that has a very high resilient to manufacturing error. We optimize the EPE so that this is a full OPC replacement, not just for assist features. And also the cost function is down in the frequency domain. So the mask pattern we generated, they're naturally symmetric. And also we implemented this curvilinear mask rule checking. So the result we generated are MRC clean. And the secret sauce for this is the GPU acceleration. We use a GPU to accelerate the computation used in IoT, for example, the litho simulations. But we didn't do the normal way people handle full chip. We basically split the full chip into all those small partitions, and you give each partition into CPU or CPU GPU. We actually came up a new way that actually solved the stitching issue that traditional way would generate. So we came up this we call gigantic CPU GPU pair. And we put the entire design in the memory, and the entire design, they're iterated in each step. Therefore, there's no stitching issues between those partition boundaries. With that, we can do a full chip, and it's a stitchless. Also at that paper, I said that this kind of a full chip curvilinear IoT mask cannot be written by VSB mask writer. We tried that at D2S before. We used the overlapping shot to reduce the shot count. We used the mask simulation to simulate those mask shape, but it didn't work. The right time or shot count is still too high. But today, I'm going to tell you something different. Those curvilinear IoT can be written by VSB mask writer for 193i. And here is a movie for the same contact array, that sequence. And on the left, you see those are the VSB shot for VSB mask writer. And on the right, those are the simulated wafer contour. And I'm going to show you the real mask and the wafer in this paper. So what's changed? What's changed is this new technology we call mask wafer co-optimization, or MWCO. In the traditional approach, we first generate the curvilinear IoT mask pattern, and we are then doing the, we call MDP, or generating the overlapping shot, so that we try to match the curved mask shape. But in this new approach, instead of trying to match the mask shape, we are going to match the wafer shape. So we call that MWCO. And this new flow actually changed the handoff between OPC and mask shop. So let me explain that. So today, in the mask shop or in the OPC shop, you take a design, you do OPC, then you generate all those decorations. It's called post-OPC, GDS or Oasis. You give that file, you through the wall to mask shop. Once mask shop take it, receive it, it will run MPC, mask process correction. It basically can be done in either rule-based or model-based, but basically apply bias to this shape. Once that's done, they do the next step they call fracture. It basically break all those patterns into rectangular shot that's used by VSB mask writer. In this new flow, we are actually going to generate a shot in the OPC shop. So we take the design at the OPC shop, we run true mask IoT with MWCO, we generate those shots. We do use a mask model, and this is a simple mask model. Once we generate those shots, we give the shot list to the mask shop. And they can do MPC using more accurate mask process model. But they don't have to do fracturing anymore because we already have the shot. So that's the difference in the flow. The one thing I want to remind you, all those masks, they are actually curvilinear, even for rectilinear OPC design. Like you see in this example, the center contact is a rectilinear, but on the simulated mask pattern is basically a circle. Then the assist feature, those staircase assist feature, actually on mask, they are those smooth angled line, angled assist feature. And we can use that to reduce the shot count. We look at the shot count for all these 91 different configurations in the conventional fracturing. Then we realized that 80% of shot, they are actually from SRAF. This is understandable because there are a lot of SRAF, and SRAF are really curvy, and if you use the conventional fracture to fracture it, you generate a lot of small shot. With that, that means if we can significantly reduce the shot count on assist feature, we can greatly reduce the total shot count or reduce the write time. So fortunately, we can do that on assist feature because assist feature, they have a less impact on the litho result. And on the main feature, they're more important. We can keep using conventional shot so that we get a better accuracy. So this is a good balance. Let's look at this example. In the conventional approach, as I explained, we first generate the overlapping shot. Then we do the conventional shot also on the main feature. Then we simulated the mask contour, trying to make that contour match the curvilinear mask shape. Then we ran the wafer simulation. We found, there for some locations like here, we actually have some EPE error, like 2 nanometer EPE error in this case. How to fix that? It's actually straightforward. Think about we can actually do double simulation. We can run mask simulation, we can run wafer simulation. So if we take the shot, we simulate all the way to wafer, then we can use that simulated wafer compared to the wafer target, then try to minimize the difference between these two. And we just have to move the shot as what we did before. It's just a cost function change. And with that simple change, we can optimize the shot to minimize the wafer EPE. So in a summary, in MWCO, we are actually doing a double simulation. We do the mask simulation first, then we do the wafer simulation first, the second, then we simulate the wafer contour, we'll minimize the wafer EPE for those shots. Since now we're targeting on the wafer, not a mask, we can even further reduce the shot count. Let's look at this example. The same contact array, 91 of them. We look at the total shot count. In the conventional fracture, we have over 1 million shots. And once we do the overlapping shot without MWCO, we actually reduce the shot count by half to like 500,000 shots. Then if we do MWCO, we can further reduce the shot count by another half. So now we have about less than 250,000 shots. Then compared to the OPC shot, which is about 200K shot, then the shot count is comparable. That means the right time is comparable to OPC. Then you look at those different configurations, you see we greatly reduce the shot count for SRAF. So those SRAF, the circular SRAF just becomes a single shot. And those curved SRAF, we just use a 5-shot overlapping shot to do this curved SRAF. So here is the real mask that actually written by VSB mask writer. So let me replay this. You see, for conventional and overlapping without MWCO, all of those main features and also that MWCO, they are reproduced very nicely, very high quality. And overlapping and conventional, they are pretty much the same. Then once we have a cis feature, then overlapping without MWCO still keeps the cis feature circular or curvilinear. But MWCO, we greatly reduce the shot count. In this case, just a single shot. And some is a couple overlapping shot. So the smallest feature over here is still like 80 nanometers. So it's quite large shot. So the mask variability, pattern variability is very small. All right, next we'd like to see if we can actually reduce the shot count to a level that VSB mask writer can actually write the entire mask faster than multi-beam. We all know multi-beam, the mask write time is a constant, about like 12 hours or half day. And for VSB mask writer, the write time is proportional to the number of shots. So it turned out there is a magic number, which is a 36 shot per square micron. So if we can keep the shot density all below 36 shots per square micron, then the entire mask can be written in 12 hours. So let's see, we still look at this array. So when the array is dense, it's just the main features, and there's some SRAF around the array. So here is mainly the shot count on the main feature. But once we have SRAF, you see the SRAF is significantly, the shot count is significantly reduced. Here is just a single shot, here is a 2 overlapping shot, and here is 4 shot. And for this curve, we use a 5-6 shot to make it. And the main feature, they're still conventional shot. So let me play this whole movie. So you see the whole sequence. Okay, then let's look at the shot count for each configuration. And it turned out for all of them, for each configuration, their shot density, they all below 36 shot per square micron, which is this green bar. That means for any real design, it's basically combination of all of those different density patterns, right? So that means since for any configuration, we can keep the shot density below 36 shot per square micron, then the real design, any real design, we can write it less than 12 hours. We then look at the process window. Last year, I showed the process window. Later on, some people said, oh, that's just for one measurement. So this year, we actually measured on 61 different patterns and size. And we measured with 7 different focuses and 9 different doses. So total 63 process conditions. We first look at the nominal condition to check whether the bias for these 3 variations, are they about the same? And also the CD distribution, we call mean to target distribution, are about the same. So here you see all of them, their mean to target, the center is about -5 nanometers. So they're about the same. And also the distribution is about the same. So that means it's a fair comparison. They are about the same at the nominal condition. We're not printing something bigger, or we don't have a bigger contact than OPC. Then let's look at this CD distribution for the entire 63 process conditions. Now we see a big difference. So overlapping without MWCO and MWCO, the CD distribution are half as OPC. So this is very significant. That means MWCO is much more resilient. We have a much smaller CD variation than OPC. Then we plot the boson curve, the process window curve. So here we include all 61 patterns and the size. And we use the percentage, like how many patterns passing the CD spec. The CD spec is 10% CD variation. And we use the color, green to red. So basically the valid process window is those green regions or non-red regions. And you can clearly see overlapping without MWCO and MWCO significantly increase the process window by 2x, especially in terms of depth focus. All right, with that, let me show you the movie I promised. So here you see on the left is the MWCO mask, the mask written by USB mask writer. On the right is the wafer print. And you see the mask has a very high quality, and also the wafer print, look at all those contacts. So the contact from the center all the way to the edge, they all printed very uniformly. So in a summary, last year, we presented our first curvilinear IoT paper. We showed that those kind of curvilinear IoT masks can be written by multi-beam mask writer. We worked together with Micron, and we printed wafer. And this year, we worked together, and we showed that those curvilinear IoT masks can be written by VSP mask writer for 193i with this new technology we call MWCO. And this is for 193i. For EUV, you still need the multi-beam because that's not just a short count issue. With that, I conclude my talk. Thank you very much for your attention.